In this chapter, we're talking about basic principles of radioactivity. Well, not principles of radioactivity, but types and so on. So, certain nuclei of certain elements are unstable due to the specific ratios between protons and neutrons, and can spontaneously go through a process called nuclear fission, which results in the production of various types of radioactive emissions. So most naturally occurring isotopes, you don't need to memorize that it's elements up to atomic number 19, but it kind of highlights that all the way up to potassium included. They're stable. Now, for elements that are, and this is not like, well, it is true, but I can give you examples of radioactive carbon, radioactive nitrogen, radioactive oxygen, radioactive phosphorus, radioactive hydrogen. So the point is, there are isotopes that have unstable nuclei, and due to the repulsion between the protons, these nuclei discombobulate, so to say, producing various types of radioactive emission. Now, a little note that they totally don't get here, but I think it's way more important than numbers. Take a look at the periodic table, please. Specifically, 6th period, groups 17 and 18. Can you see those? Astatine and radon. You see the atomic masses at the bottom? They are in the brackets, right? It means that this is the most frequent isotope and it's radioactive. When it is in brackets, it's given for the most stable radioactive isotope. And it means that there are no isotopes that are not radioactive. For instance, if you will take a look at the element number 92, which is the bottom row, uranium, okay, 92. Uranium has stable and unstable radioactive isotopes. But we can see, there's a stable number. Neptunium, on the other hand, next to uranium, only has radioactive isotopes. So a definition of a radioisotope is that it has an unstable nucleus and emits radiation. Can be one isotope, can be many. But when we talk about those isotopes, we always include the mass number in the name of the isotope. So here's a really good example, okay? So carbon-14. If I tell you that the reaction between carbon and oxygen, I don't specify which carbon it is. But if I talk about radioactivity, I always must mention which atomic mass we're talking about, okay? So carbon-14. Now, the radiation that can be emitted during the fission process can be broadly divided into, I divide it in 3 types. You will see why. So first type is alpha particles. Alpha particles are nuclei of the element helium and contain 2 protons and 2 neutrons, okay? Then we have electrons and positrons, or beta negative and beta positive radiation, okay? So beta negative and beta positive. The only difference between the particles called electrons and the particles called positrons is the charge. Electrons are negatively charged, positrons are positively charged. All other characteristics are exactly the same. And finally, we have gamma emission, or gamma rays. These are electromagnetic waves. And this can be reflected if you take a look at this. So alpha particles, right? The atomic mass is 4, 2 protons, 2 neutrons, and the charge is 2 because there are 2 protons. Then you look at the electrons and positrons. What is the mass? 0. Okay? But there is a charge at the bottom. -1, +1. And finally, you look at gamma rays, and what does it tell you? It tells you that the charge is 0 and the mass in a conventional way is also 0. Questions? We good? Okay. So let's talk about alpha particle. So alpha particle is effectively the nucleus of an element helium. It contains 2 protons, which makes it charged, specifically charged to positive, and also 2 neutrons. So when we combine 2 protons and 2 neutrons, the mass number of that particle is 4. It can be ascribed this symbol or this symbol. An important feature of alpha emissions is that they usually have fairly low energy. I myself think about them as a really big particles that fly, quote unquote, move, quote unquote, slowly. Okay? So this low energy, though, should not trick you, because alpha radiation can become very dangerous. Now, beta particles. Beta negative particle is an electron. I want to remind you, electrons do have mass, but it is so small that we do not even take it into consideration when we think about electrons. So we ascribe the mass number of 0 to them and the charge of -1. So when a neutron with the mass of 1 and the charge of 0 changes into a proton with the mass of 1 and the charge of 0. Sorry, and the charge of +1, that's my bad. We need to compensate that positive charge so that the balance of charges on both sides would be 0, right? So this is why an electron with the mass of 0 and the charge of -1 is produced. If you will look at the charges and the masses on both sides of the equation, you can see that there is mass of 1 on the left, and there is a charge of 0 on both the left and the right, altogether. Positrons, okay, this is the sort of antagonist of an electron. It is a particle that has a mass the same as electron does, but has a charge of +1 and -1. So we can describe the reaction in which electron is formed as like this. So when a proton with a mass of 1 and the charge of 1 changes in a neutron with a mass of 1 and the charge of 0, we have to maintain charges by the effectively electron with the charge of plus 1 and the mass of 0. Okay? Now, what about gamma rays? Gamma rays are just like any other. It's like a visible light. It's waves. So high energy electromagnetic radiation. Mass number is 0 and the charge is 0. So that happens when an unstable nucleus has to dissipate some energy while becoming a more stable nucleus. So here we're going to basically write down the symbols for alpha particles, beta particles, and so on. So for alpha particle, I'm not going to use helium because it's an element. I'm going to use alpha. But since it's identical to the helium nucleus, what is the charge of the helium nucleus? Periodic table is right there. It's element number 2. So if the atomic number is 2, how many protons do we have? 2. And since mass number is about 4, so how many protons plus neutrons we have? 4. Mass number is 4, so it's 2 and 2, okay? Positron, positively charged electron, right? So 0 mass plus 1 charge. Beta particle is your garden variety electron with a mass of 0 and the negative charge. Neutrons, now they have the charge of 0 and the mass of 1. And finally gamma rays with both mass and the charge of 0. Now you may wonder why we have neutrons in this list, right? Turns out that during nuclear chain reaction, the one that actually results in atomic explosion, for example, neutrons are emitted out of the nuclei when nuclei break down. And they are essential, those neutrons, to maintain the chain reaction, okay? So basically, I know that maybe I'm jumping a little bit ahead, but when somebody says nuclear, you probably think about the atomic bomb, right? To some extent, yes. So anyone knows where is the closest power plant, nuclear power plant to us? No? Perry, Ohio. What was your version? Oh, no, they don't know. It's Perry, Ohio. They need a lot of water. That's why Lake Erie. Okay? What happens right now in that nuclear power plant is an atomic explosion, but extremely slow. That's it. Because the neutrons that are produced during binary fission by uranium are slowed down. Hypothetically, if you pull out the slowing elements, the graphite rods, you can have a nuclear explosion. Okay? So radiation obviously has some biological effects. Okay? So it hits mostly DNA. Okay? Right now, I'm going to turn on my biology instructor, call half of that chemistry BS, and just cut the crap. Okay? So all cells are sensitive to radiation. the problem with rapidly dividing cells is that the DNA is damaged. And when DNA is damaged, it may be incompatible with cell survival. Very good. So when people who have cancer undergo the radiation therapy, the principle is exactly the same. Cancer cells divide very fast. This is why if we have the avalanche accumulation of damage in the DNA of those cells, they're not going to be able to reproduce and simply die. Okay? Unfortunately, if that radiation acts on other fast-dividing cells, for instance in people's nose or mouth or gut or bone marrow, those cells will die also, and people may lose, may have altered olfaction, altered taste. They will become leukemic because, well, actually leukopenic, because and anemic, so red blood cells will suffer, white blood cells will suffer, and they're going to have GI problems, okay? So while normal tissue divides at a slower rate, the main problem with the radiation therapy is, although it kills cancer cells, it may result in a minor damage in the normal tissue, and that minor damage in turn can lead that normal tissue to turn into cancerous tissue. Right now, though, tumor treatments are done in a manner that minimizes the damage to the surrounding tissue. Usually it's done by gamma radiation, but this gamma radiation is focused. So instead of a massive, general just exposure, it is almost literally a gamma ray beam that hits the tumor, okay? So how do you protect yourself from radiation? There are three main considerations: distance, time, and the barrier, okay? The farther you are, the better. If you have a protection, a layer, that's great. And if you can minimize your exposure, that's the third part. So, distance, time, and protection. So alpha radiation can be completely stopped by clothing. It is true. Gamma radiation can be completely stopped by concrete or lead, sometimes an iron. Yes, it is also true. However, the statement for beta particles is not correct. Beta particles is a spectrum. For example, phosphorus 33, the stable isotope is 31. Phosphorus 33 is beta particle emitter, and so is phosphorus 32. You can work with phosphorus 33 on the bench without any shielding. If you would do it with phosphorus 32, you would receive a decent amount of radioactive exposure because the energy of those beta particles is different from one to another. Okay? I'm just telling you how I know that. In my career, I worked with radioactive carbon and radioactive phosphorus and was sort of tangentially exposed. My wife worked with radioactive technetium. So I know this stuff, and I did. So basically for beta, it can be different. Okay? So this person right here doesn't appear to be working with whatever they're working on the bench. So obviously, clothing is not enough. The usual protection for beta emitters is the plexiglass shield. You can see that plexiglass shield in front of the person, right? Does that make sense? Okay. So, alpha particle, true. Gamma ray, true-ish, okay? Half a kilometer, the farther you are, the lower effects are going to be. Okay, so for instance, if you are, let me put it this way, even if we remove all other factors that emerge during the atomic explosion, simple gamma radiation at the distance of half kilometer is going to kill you overnight. So it all depends on the energy and the amount. And same is true for beta particles. Phosphorus 32, I can open the source one end of the room, and the Geiger counter will be triggered on another end of the room. And that's more than 3 meters. Okay? For the sake of, I don't want to comply with bullshit. So, no, lab coats and gloves will protect you only if you work with a very low energy meters. For instance, carbon 13 and carbon 14. They are low energy. I work with 13, you work with it on the bench. As I mentioned, phosphorus 32, plastic shield. Other than that, that's correct. Okay? What I wanted to do this. Okay. So, heavy clothing, plastic shield, in reality, that's going to be what? Beta. Okay? Paper, lead, gamma. The more dramatic it is, the worse the exposure. Lab coat, not what's in the lecture, but what I really told you. Is lab coat clothing? Yeah. Wait a minute, what just happened? Okay. Alpha. Thick concrete. So you already did the radiation measurement, okay? So Geiger counters, okay? Geiger counters detect beta and gamma, which is good because alphas are not particularly dramatic. So what effectively happens when gamma rays or electrons or positrons hit this tube, this probe here, they form ions. And these ions are registered as an electrical current and give you counts. So the radiation is measured, now hear me out. The radiation is measured in Becquerel and Curie. We have to understand that there are different aspects of measuring the radiation. Okay? I'm going to give you an analogy, as always. So Becquerel was the guy who discovered radioactivity as a concept. But Marie Curie and Paul Curie, they kind of developed it, and this is why they got Nobel Prize. So Becquerel is the international system unit of radioactivity, which is very simple. 1 disintegration of any kind per second. Make sense? It means that there is a nucleus, and nucleus falls apart, and that happens over 1 second, okay? Now, Curie is the unit that shows the number of disintegrations per second in 1 gram of radium, the element that Marie Curie actually discovered, and partially due to which she died. She died of leukemia. So Curie is 37 billion disintegrations per second. Is that a huge number? It is. Okay? I can give you an idea. When I was working with radioactivity, we received like a radioactively labeled chemicals that we needed, and every shipment was measured in curies, and it was 60 to 80 millicuries, 1,000, and that was enough for about 5 chemistry labs for a week. So Curie is an enormous amount of radioactivity, okay? Now, RAD, radiation absorbed dose. So here's the thing. Imagine a bullet, right? A bullet is not super heavy, right? So if I will throw a bullet at someone, they're going to be fine, right? If I shoot someone, they're not going to be fine. But hear me out. If I, okay, let it be me who's getting shot, okay? If I get shot in the foot, am I going to die? Probably no. If I get shot in the abdomen with 1 bullet, am I going to die? Maybe. If I get shot in the abdomen with 70 bullets, I'm dead. So it shows you that different body parts have different quote-unquote importance, right? And the number of the amount of radiation will be different, okay? And the quality of radiation will also impact this. I would much rather get exposed to, for like 5 seconds, to 60 millicuries of beta than 60 millicuries of gamma. Okay, make sense? So, radiation equivalent in humans, it's not just absorbed dose, but as we just figured out, the dose of alpha radiation, if my skin absorbs alpha radiation, versus beta radiation, those are 2 different things. Okay? So we are interested in the damage. Make sense? So, alpha particles do not penetrate the skin. However, if the alpha source gets absorbed in the body, am I making sense right now? It will create an absolute havoc. It is inside the body. It is when there is no skin protection, when there are living cells. It's one of the most damaging types of radiation. Okay? High energy radiation, more damage. And gamma rays are the most damaging. Sounds good? So there is a factor which you should use when you calculate the degree of the biological damage. You can calculate the absorbed dose, which will be based on what? Let's say this bottle, the time, this bottle is radioactive. It's not, but let's say. Who is currently receiving greater dose, Sarah or I? Me, why? Closer, yeah. So distance, time, shielding, it all impacts the absorbed dose, okay? But then there's a biological effect. If I have carbon 13 in this bottle, I'm not concerned. This plastic will absorb all of it, okay? Or, okay, the distance, the energy still not too dangerous. Make sense? If I have alpha source, I'm even less concerned. Okay, if it's gamma, it's a problem. So, for beta and gamma, we factor it 1. Okay? For neutrons and protons, think of them as little particles that fly with immense speed and trash anything in their path. This is why the factor is 10. They're more dangerous, but neutrons are rarely emitted when we work with like normal sources of radiation. And for alpha, the factor is 20, and you may wonder, why is that so? If it's such a low energy thing. Because, hear me out, alpha, if it exists outside of the body, there is no absorbed dose for it. It cannot get through the skin, through the layer of dead cells. It's not getting in. It's not absorbed at all. On the other hand, when it gets inside, we've got a problem. Before we get to this, I'm going to illustrate that for you. I want you to take a look at periodic table. Okay? Second group, yeah, the bottom, the very bottom, it's radium. Radium was discovered by Marie Curie, and it's an alpha source. Okay? It was pretty safe to work with. The only problem is that radium is in the same group as calcium, which is the major mineral component of our bones. When she passed away, she was buried in a lead coffin because her remains are highly radioactive. Not only because of radium, okay? There is another element, he actually worked with it on Monday, strontium-90, okay? Strontium-90 is alpha emitter, among other things. It can replace calcium in the bones just like radium can, and it becomes a problem. Does that make sense? Another thing that I want to highlight, ever heard about the story of women who worked at the watch factories? Yeah? I think, Radium Girls. I think there's a movie. Yeah. So back then, I'm blanking on the English word. The clock, the what? All the numbers and what do you call it? The clock? The face. Thank you. Yes, the face. The face of the clock. All the numbers, all the lines were painted by hand. And to make the numbers and the lines shine in the dark, the paint contained radium. Its biological effects were unknown yet. So women who did that work, they used their saliva to sharpen the little brushes. So they transferred a significant amount of radium-containing ink on their tongues, which are not protected by the layer of, dead epidermis, and all of them died of cancer. Pretty much all of them. Okay? So, if you work with radiation, you're going to wear a dosimeter. Okay? This little device to be we had to wear dosimeters. I think I constantly forgot to wear them when I was working in research, but we were very careful. So dosimeters will measure all types of radiation, okay? And there are certain limits. Now, to how much radiation you should be exposed over in a matter of year. Now, I personally think that people who do the units in radiation, they went completely bananas, okay? Because in addition to Curie, Becquerel, Rad, and Rem, there are also Grays and Sieverts, okay? So this is the accumulated dose over the year. SV stands for Sievert, and this is the average number for a person here, okay? It's a very small number. Concrete buildings. Concrete normally contains significant amount of thorium, element with the atomic number 90, and some concretes contain more than others. When thorium, the radioactive isotope of thorium, breaks down, it releases the gas called radon. Number 86, you probably have heard about the radon inspections. That's exactly because of the concrete basements. Okay? Food and water, there's some, the air, obviously. But we do not receive a lot, cosmic radiation because it's far and because there's an ozone layer. There is some degree. Now, potassium-40, folks, potassium is fairly common in foods, and it does have unstable radioactive isotope potassium-40, but like we do eat some radioactive carbon and some radioactive phosphorus, but the amounts are very, very small, okay? Obviously, X-rays, CT scans, okay, mammograms, but also there's one thing that they're missing here. So remember the distance idea of protecting yourself from radiation? So I'm going to ask you a series of very stupid questions. You be okay with that? So the cosmic rays, where do they come from? Cosmic rays. Oh, cosmos is the word for outer space. Right? They come from the outer space, from beyond the atmosphere, right? How can we get closer to the outer space? Can you get closer to the outer space? I almost bet that everybody in this room did that at least once in their life. Probably more. Huh? Airplane. People who fly a lot, and I mean a lot, their radiation exposure is significantly higher. I'm not talking about, like you fly 6 times a year to your grandma or for a vacation. I'm talking about, like, I have a buddy who easily can fly across the globe in a week, giving talks different places, So, couple of, that's air travel. They should stop doing this. No. It's not condescending. You're not old enough, I think, to remember the big ass TVs with the tiny screens and those screens was real fun to, if you find one at a landfill, you just break it, okay? Garbage can, it's so fun because it's vacuum inside and it's, They did emit beta radiation normally because they used electrons. Not anymore. We only use those. You may find those in some old medical equipment or lab equipment, but that's really nothing. this. In reality, zero, folks, zero. We do not receive any radioactive exposure from power plants if everything is properly contained. I'm not talking about, the issue with the storage of nuclear waste. It's a separate, very interesting, very depressing story. But okay, radiation sickness. When the explosion at the Chernobyl nuclear power plant happened, I was 7. So I remember all the stories and the cover-ups and people suffering from that. There is, I don't know if you watched I think it's HBO show, Chernobyl. It's pretty accurate, okay? It's actually very accurate of what it was like and what was happening there. Of course, there were people, I don't know if I didn't watch the show, but there were stories of firefighters who used helicopters to extinguish fires. And they flew over the exposed reactor and died next day of radiation exposure. It was enormous, okay? So 1 sievert will give you short leukopenia. More than 1 sievert will cause severe exposure. 5 sievert is the median lethal dose, okay? So 50% of people who are exposed to this will die. Now, let's talk about symptoms very quickly. Nausea and vomiting. Why? Because your stomach and intestinal lining are screwed. Those cells divide very quickly, and now they can't. Okay? Fatigue and reduced white cell counts. Your bone marrow is damaged, so you have both a reduction in red and white blood cells. They don't mention skin lesions. Skin contains pretty fast dividing cells as well, so extreme exposure can result in skin lesions as well. So, yes, we are pretty gentle species, okay? Now, I want to emphasize that unit, sievert, it does account for the body size. Does that make sense? Okay? So, you can see that mammals are pretty gentle. It's very complicated. Sophisticated things are more prone to damage. But what makes me happy, even if nuclear war is going to happen, which I wouldn't oppose to, bacteria and cockroaches will survive. And for me, this is the most important thing, because life will persist. Okay? Maybe the second try will produce something better than us. Okay? So this is the term LD, lethal dose, and you see the number 50 as a subscript, median lethal dose, the dose that kills 50% of the cohort. Okay? There's, by the way, I really like that they use bacterium, because there are bacteria that can be easily destroyed by UV light. And there is a species of bacteria called the Deinococcus radiodurans, which was isolated from the cooling circle of a nuclear power plant. It, lives in radiation. It is exposed to neutrons and gamma rays on a daily basis, and it absolutely thrives there. Okay? It doesn't infect humans. This is actually a very interesting topic, the irradiation of foods. Okay? So, salmonella, about 30,000 cases a year in the United States. If you ever had salmonellosis, you will remember it for the rest of your life. I do. E. coli. Enormous number of cases. Ever heard about the outbreaks associated with things like Roman salad or bean sprouts? That's E. coli O7H157 strain. Centrohemorrhagic E. coli. It's a very dangerous microorganism, but the main source is actually ground beef. Seriously. Listeria, a very tricky pathogen that can spoil foods. There are always some outbreaks of listeria. It is not a garden variety gastrointestinal infection. I had a student in other class who had listeria during the semester. 2 weeks in the hospital, a week in ICU, and she lost her fetus. She was pregnant. It's pretty common. If a pregnant woman gets listeria, probably that's it for the fetus. So, cobalt and cesium are used to treat foods. Foods do not become radioactive. Please understand that, okay? So, you can find the image, but it's pretty much like when you, at the airport, when you go through security and you run your suitcase on those rolls, that's what it looks like. Those are just rolls, okay? Now, if you wonder, I'm going to rant a little. So mushrooms, they stay okay fairly long. Strawberries, I don't think so. Every time we buy strawberries, 2 days later, we throw them out. Okay? Tomatoes, blueberries. I cannot say anything about blueberries. So, the food does not become radioactive if it's irradiated. Okay? It's not. It's good. But I'm going to give you another detail that very few people know. It's not a common knowledge. Does anyone like mangoes? Yeah? Yeah, sure. Yeah, mangoes grow not in the United States, but in Central and South America. You know who else likes mangoes? Fruit flies. And they deposit eggs in the skin of mango, and then those eggs produce larvae, which are small white worms, which can go through your gastrointestinal tract and not disintegrate. They're going to die, but in your feces they will appear as relatively small white worms, which can freak the living shit out of you.
And where's this from?
Mangoes. This is why mangoes that are imported in the United States are irradiated to kill eggs. Okay, so there will be no larvae. Make sense? So, half-life. We need to figure out what is a half-life. So, the time that it takes for radiation to decrease to 1/2 of its original number. So here's an example of half-life using iodine-131. I believe it's the gamma source. So you start, and I'm going to make it a little bit more complicated than this image. Let's say you have just some kind of a sample which contains 20 milligrams of that isotope. In whatever time the half-life is, you go from 20 to 10 milligrams of that isotope. You may ask, wait a second, the other 10 milligrams, where did they go? During the radioactive decay, they became a different element. Make sense? I would argue tellurium? Probably, but I'm not entirely sure. Okay? Does that make sense? And whatever was changed, neutrons maybe got emitted or whatever, okay? And then another half-life, it's half of 10, and another half-life, it's half of 5, okay? So it's not 10 milligrams every half-life. You cut it in half. That means that the decay curve is, it can be categorized as a logarithmic curve, okay? That makes sense. So if half-life is 8 days, then in 40 days, the amount of radioactive iodine left in the sample will be decreased 32 times. Not going to go into calculations details, but 32 times. So here's my question. Let's say you work with iodine 131 and you accidentally spill it on yourself. Okay? Let's make it a real life scenario. You are in the lab and you spill iodine, radioactive iodine, on yourself. What do you do first? No, absolutely not. The very first thing that you do is you pull out your phone.
Do what?
You don't move anywhere and pull out your phone. And you call, while standing still, the radiation safety people. They come over, look at you, undress you, or take whatever is contaminated off of you, put it in a bag, put it in a container, then they might wash you, decontaminate the area. Are you going to get those clothes back? What? Okay. Every 8 days, it decays twice. In 80 days, the amount of radioactivity will decrease more than 1,000 times. In 160 days, it's going to be more than 1 million times. They may keep your clothes for 6 months and give it back to you. And you're fine. Does that make sense? Now, the reason why you should stand still. This is the real case, happened at the University of Nebraska-Lincoln, where I worked for a little bit. It was before me. Person spills radioactivity on the floor. And instead of calling radiation safety people, they decide to find someone. So they go in the hallway, walk back and forth, don't find anyone, come back, finally give a call to somebody else. They say, that's a stupid idea, call radiation safety people. They had to shut down that floor for several months because there was no way to decontaminate it. Good thing it was phosphorus 32. Its half-life is 14, give or take 14 days. So they basically waited for like 6 months for radioactivity to just go away. Okay? Does that make sense? So the first thing, you do not go anywhere. I mean, if you have to go to a lab phone, sure. But you want the radioactivity to be as contained as possible. Okay? So, some half-lives. Okay? Carbon-14. Very low energy beta, so not a huge deal. Potassium-40. The only concern is gamma, but we get it from food, so whatever. This is your Marie Curie. She died in what, like 1930s, 40s? Yeah, she's going to stay radioactive for a very, very long time. Okay? By the way, all her lab notebooks, all her lab belongings, they are stored in the special boxes, the lead boxes. Strontium-19, 38 years, okay? So we talked about it as an element that can replace calcium in the bones and stay in the bones for a long period of time. So if you think about this, somebody gets enough strontium inside, they're going to die before that radioactive period. That half-life will end. Uranium-238. This is the one that's used in, let me see. Oh yeah, no, I think 235 is used in a nuclear bomb. Medical isotopes, carbon-11, 20 minutes. Have you heard about positron emission tomography or PET scans? No? You're given a compound that contains carbon-11, it circulates through you, gives you special type of imaging, okay? I don't remember exactly. You can basically measure very specific activities in very specific organs, but the point is, you receive it, by the time you leave the facility, it's gone, okay? Chromium-51, I believe it's for sort of gamma ray treatment of tumors. Iodine-131, anyone knows what it is used for? There is an organ in the human body which produces a compound that requires iodine. People with iodine deficiency have a condition about that. It's good that you don't know, because we don't have iodine deficiency. The condition is called goiter, and the organ that I'm talking about is thyroid gland. It produces thyroid hormone and requires iodine in the food. That makes sense? So that radioactive iodine that emits gamma rays, will it go the same place as the normal iodine would in the thyroid gland? No. Remember, chemically, isotopes are identical. Am I making sense? Iodine-131 will get into thyroid gland. What do you think it's going to do to thyroid gland? It's inside, and it's radioactive, and there's no shield. What's going to happen?
Break the cells down.
It's going to kill it. This is the treatment for thyroid cancer. It's much easier to, and half-life of 8 days means that eventually that person will not be radioactive. Am I clear? So that's the idea. Technetium is used very actively for treatment of cancer. Okay, medical applications. That the illustration that I gave you, thyroid gland. Okay, no differentiation between non-radioactive and radioactive. Okay, and then you can detect that radioactivity. I'm not going to read the table for you if you don't mind. Okay, so this is what happens when people with chemical education start writing medical things. Thyroid cancer. Nobody in their right mind treats hyperthyroidism with iodine. There are drugs. Okay? There are drugs. Overall, if you look at all those radioisotopes, their half-life is pretty short. Okay? That makes sense. You can administer those isotopes to people, and then after some time, they're not radioactive and they can go out and live their life. Okay? Does that make sense? So I'm just not gonna, okay. Scanning. Yes, if it's a specific isotope, it usually targets a particular organ. So the scanner the gamma or beta will produce the scan. Nobody uses photographic plates anymore. I don't know if you ever actually encountered those. Everything goes on the special screens, that, or even imaging machines that like will immediately convert it into an image on the screen, so there's no sort of paper trail. Okay, so this is thyroid scan. Okay, using iodine 131. This is what I was talking about, positron emission tomography. Okay, so the compound that is, the isotope that is used for it is carbon-11, which has a half-life of 20 minutes. So when you give the glucose that contains such carbon to a person, for instance, the regions of the brain that are active will utilize a lot of glucose. Does that make sense? All good? So in that image, for instance, I'm trying to find, yeah, probably this color. In that image, the blue areas represent ventricles in the brain. So the rest, the bright stuff, represents the tissue, active tissue that consumes glucose and breaks it down. Neurons are very metabolically active. This area on the right scan is where there is no activity. So the neurons are dead. It's the consequence of a stroke or Alzheimer's or whatever, you know. So other potential sources include oxygen 15, nitrogen 13, fluorine 18. Why do you need that variety? Because for different organs, you may use different compounds. For example, you can label glucose, which is fine, or maybe you need to take a look at some amino acid processing in liver, okay, very specific part. In this case, you may use nitrogen or oxygen, okay? So positrons, when they are released, I really like the use of the word combine, but much more impressive word is annihilation. Positrons and electrons, when they combine, they destroy each other, okay? And I can prove it to you by writing a reaction, a nuclear reaction of annihilation. So positron has no mass with the charge +1. Electron has no mass and the charge of -1. When you combine them, still no mass and no charge. That's gamma rays. Okay? Now, computed tomography, I would accept this as being a technique based on radiation, sure. X-ray, which is essentially a type of radiation. X-rays are electromagnetic waves. They have lower energy than gamma rays because they have lower frequency, but they still not good. Like, they can cause damage. Okay, they consider to be a type of radiation. And then, you know, that's the yellow tumor in the brain. Okay, CT scan. Okay. Now, this is a bit of a stretch, to say the least. Is this a radiation imaging? In a way, yes. Does it have any relevance to the things that we just discussed? Not really, because MRI stands for magnetic resonance imaging, right? Make sense? All you need for this is a magnetic field. It is safe, and and I think it's most expensive because the devices, the machines are extremely expensive. Hospitals have to sort of pay them back, and they most expensive because of the magnets. Okay, the magnetic fields that are produced in MRI machine. This is why you have to answer, do you have any metal in your body? Okay, there are a lot of prosthetics that are kept inside. Okay, they made out of, is it diamagnetic paramagnetic? I can't remember the term, diamagnetic or paramagnetic. So basically metals like titanium that are not magnetic. Okay, and what is the main component of the tattoo ink? Not the main, but one of it's iron. You will survive. I will survive, but it's going to burn as hell because that magnetic field will start pulling those particles, those iron particles, out of the skin. It will not succeed because they're very, very small, but it is painful. Okay? Questions? All right.